The policy of the Royal Electrical and Mechanical Engineers for broken down or battle damaged equipment is to complete the repair as far forward on the battlefield as resources and the tactical situation permits. The aim of the Corps in war is to put repaired equipments back into the hands of the user as soon as possible and to keep them there. In achieving this aim, we must assess the problems, find out what the real needs of the user are, and tell him accurately how long it will take to achieve. To fulfill our task, it may be necessary to use unconventional repair techniques, using the most up-to-date technology available, including tools, test equipment, and materials. These repairs will not necessarily be to peacetime standards, and may be limited to certain essential systems within an equipment to allow it to complete perhaps just one more mission. In war, the enemy will not allow us the time to adapt. Therefore, our training must ensure that tradesmen will change rapidly from peacetime standards to the unconventional repair techniques necessary to keep equipment in the hands of the user. Proper assessment of a casualty is the key to a successful repair. Only after a thorough assessment is carried out can an accurate time of completion be given. The senior technical person on the ground will generally be an artificer. Not only will he be responsible for all technical matters, he will have to consider what resources are available, including technical knowledge, spare parts, AESPs, manpower, and time. He will also have to consider logistics, fuels, and lubricants, and know the tactical situation. He might also be forced to interchange trade disciplines in order to complete the assessment and then give an accurate time of completion for the repair. With the ever-increasing complexity of today's equipments and the greater reliance of the user on them, it is vital that tradesmen of all discipline fully understand the equipments they repair, to enable them to bypass sub-assemblies that are broken or damaged, to allow the equipment to continue in its operational role. This may require tradesmen to spend more time on more complicated equipments than they do at present. We must continually ask the questions what, why, when, where, and how of battle damage repair. What is battle damage repair? BDR is the unconventional repair of unfit equipment that will allow it to be returned to the user quickly. Why do we need BDR? To increase equipment availability to the user during times of hostile activity. When and where do we practice BDR? During courses, exercises, and on-the-job training at work. How do we achieve BDR? By continuous training, influencing equipment design and the development of repair techniques. All parts of an army must train for war. Therefore, the Corps must ensure that the skills necessary in times of war are properly developed in peacetime, and that we have the available up-to-date tools, test equipment, and materials to ensure that the user has his equipment when he most needs it.
In recent years, battle damage repair exercises have been held in West Germany with British, American and German forces taking part. The aim being to subject various equipments to the type of damage that could be expected from direct and indirect enemy fire, and to then assess and repair the damaged equipment in a minimum of time and using a minimum of means. The study of the damage caused and the methods used in achieving the repair made it evident that there are 3 stages to battle damage repair. These are assessment, decision and repair. Of these 3, assessment is the single most important. If your assessment is incorrect or incomplete, you may decide on the basis of the incorrect assessment to commit part of your labour force and repair resources to an equipment that cannot be made even partially operational within the time estimate that the user will undoubtedly require from you. Assessment of battlefield damage from enemy fire, accident or normal breakdown must be accurate. The first rule of assessment is to trace the path of each round or piece of shrapnel from its entry point to its exit point or to where in the equipment it became spent, noting the damage caused down its path. Following the paths of these 2 7.62mm rounds, the top one passed through the air cleaner and severed the generator drive belts, chipping the pulley on its way. No further damage could be attributed to this round, and the generator was still serviceable. The lower round passed beneath the air cleaner and generator, but severed both main hydraulic brake pipes and damaged the lighting harness. It entered the cab of the vehicle, missing this screened harness. It passed on through the seat block and became spent, having caused no further damage. When assessing an equipment, look for secondary damage around a component that has been hit. For example, here the obvious damage is to the steering track rod and the front axle casing. It wasn't discovered until much later that the radiator, which had also been hit during the shoot, had suffered secondary damage caused by splinters flying off the track rod. When the radiator was being filled prior to a pressure test, a leak appeared before the water level had reached the major repairs. On investigation, these splinter holes were found. This type of omission from the assessment will obviously extend the repair time of the equipment. Be aware of and trace the path of ricochets. Here a round ricocheted off the exhaust manifold. It exited harmlessly through the bonnet. Nevertheless, a ricochet could be more destructive than a direct hit, and more difficult to trace. As an armour-piercing round exits through armour, splashback can occur. This is where small splinters of hot metal from the inner side of the vehicle armour fly back into the hull or turret, and tend to embed themselves behind and into cables and components. To demonstrate the point, follow this graphical representation of what happened during the opening sequence of this video, when a chieftain was taking hits from armour-piercing rounds. It should be mentioned that multiple shots in the same area will lead to a reduction in the integrity of the armour, but of course, in action, the likelihood of such a situation would be remote. This round bounced off. The next one penetrated the turret armour, spreading splinters off the interior of the turret wall. These cause obvious areas of damage that were readily noted by the assessor. When the round exited through the rear of the turret, small splinters or slivers of metal tended to fly back into the compartment. Although these splinters caused mostly minor faults, they were very difficult to locate. This type of hidden damage, if not located in the initial stages of an assessment, can and will prolong a repair time quite considerably. The final rule to follow when assessing an equipment is do not make assumptions. You must follow, investigate, and prove what damage a round or piece of shrapnel actually did. Here an assumption was made that the cause of this seized engine was this round, which had penetrated the sump. When the sump was removed, this assumption was proved wrong. In fact, it was this round, which had not been traced properly. It had pierced the cylinder block and embedded itself in the number 2 cylinder liner, halting the movement of the piston halfway up the bore. This round caused another assumption to be made at the beginning of the assessment, that the engine had not in fact seized. From this graphical representation, you can see that the position of the round does allow a certain revolution of the engine. While this assumption was quite quickly disproved once the engine turning handle had been used, it does serve to illustrate the point that it is easy to jump to the wrong conclusion. An assessment may need to be divided into 2 stages, primary and secondary. Dependent on where an equipment has taken a hit, a primary assessment may be all that is required. Alternatively, it may require both primary and secondary assessments. Earlier you saw this chieftain being damaged by an anti-tank mine. All the effects of the blast were centred on the running gear, and it required only one assessment to note all the damage. This 432 has taken a single armour-piercing round through the front armour. The primary assessment traces the path of the round through the armour, noting the severed rear generator engine services and firewire cables, and the entry point into the power pack through the power pack junction. It is obvious at this stage that a secondary assessment is required, and that to carry it out, it is necessary to remove the power pack. When carrying out a primary assessment, only the necessary access plates or covers are to be removed. A secondary assessment is carried out by removing the minimum components or assemblies to allow the assessment to continue. This will take time and resources, and may necessitate a change of location and the use of recovery vehicles. It should be noted that when carrying out an assessment, you must be prepared to record the damage caused to the complete equipment. And not just the damage within your own trade discipline. To enable you to do this, you will need to identify components and systems which do not necessarily fall within your own trade responsibility. This assessment of chieftain turret damage should serve to illustrate the point. Internal entry point. This is the top of the SA cam adjuster. This, the commander's fire control unit. These are the cables above the commander's control and monitor unit. This is the turret ring. Now you have sufficient information about how to carry out an assessment. The next, very important step is safety. Having been tasked to look at an equipment on or near the battlefield, approach it with caution. Is there any further danger from enemy action? Fire or explosion? If the vehicle has spent time in enemy territory during the ebb and flow of a battle and has not been destroyed, it may be booby-trapped, which would take little time to rig and could have disastrous effects on you and the equipment, as this smoke grenade demonstrates. Before entering the vehicle, be aware that you can expect to find the remains of the dead. Look for weapons which may have been damaged or left in a dangerous state. Look for bare electrical cables that may still be live and could short out if disturbed. Look for ammunition which may be in a dangerous state, and fuel or oil spillage. Do not attempt to switch on or operate any system until your assessment is complete. Disconnect batteries or power supplies as a first IA where practicable. To summarize, these are the main points you will need to remember to carry out an accurate assessment. The rules of assessment. Trace each round from its entry point to where it became spent. Look for secondary damage around components that have been hit. Look for and trace the path of ricochets. Be aware of and search for damage caused by splashback. Do not make assumptions or jump to conclusions. You will end up wasting time and manpower. An assessment may need to be done in 2 stages. Again, this will take time, manpower and resources. If you're the man on the spot, you need to have the ability to report on all the damage caused. You are an important asset, so remember, when you approach a damaged equipment, look for and be aware of continuing enemy action, the risk of fire, explosion, or in certain circumstances, booby traps. On entering an equipment, you may find disturbing sights or scenes. You may find damaged weapons and ammunition which are in a dangerous state. There may be fuel spillage, damaged electrical cables which are still live. Don't try to switch on or start up systems until your assessment is complete. And do switch off power supplies as a first IA. The ability to achieve repairs to battle-winning equipments in difficult conditions and in limited periods of time relies upon the accuracy and completeness of the assessment. At the beginning of this program, it was stated that there are 3 stages to achieving a battle damage repair: assessment, decision, and repair. The next section deals with the many factors involved with the decision. Allowing for the inevitable casualties of war, the repair decision will have to be made by the senior member of the fitter section on the ground at the time. When making a repair decision, the following factors need to be taken into account. User requirement. The local commander will tell you what he wants. Followed by resources. The availability of any support from the repair system, and the conditions which prevail at the time. Now let's take a look at these factors in greater detail. User requirement. The local commander will tell you what priority he places on various equipments. He should also be aware of the tactical situation. Consider how repairs you need to effect can change according to the situation during a withdrawal. The need to bring as many repairable equipments with you as possible could concentrate your efforts on automotive systems and running gear. A holding action would probably give weapon systems priority. An advance would require all systems to be in at least partial operation. Next, take stock of your repair resources. These can be listed as manpower, time, tools, materials, and spares. These last 4 are finite resources, and you will have to make the best of what you have. Manpower, however, can stand closer scrutiny. Your first choice, in peace or war, will be the correct man for the job. However, consider the situation where a tradesman has 2 or more jobs on at the same time. Using 1 or more men of other trades working under his supervision could achieve repairs to more equipment in less time. If the correct tradesman has become a casualty, then another trade may need to be employed to do the best he can. One more option is, of course, the user of the equipment, working under supervision. Tied in with manpower is the knowledge of the tradesman and the information contained in ASPs or REMEs. Repairs could be achieved by personnel with little intimate knowledge of an equipment, referring to ASPs and EMAs in the form of microfiche. Next, support. The location and availability of repair resources from the A1 and A2 echelons, second line, and possibly other units in your area will again affect the repair decision. The conditions under which the repair is to be made will have to be taken into consideration: weather and ground. The confusion which will be an inevitable factor in and around the battlefield, rapidly changing scenarios, orders, and quick moves. Reduced communications. This will include both radio and movement. It is unlikely that you will be able to go back to A2 echelon for what you need. Disrupted supply chains. Note here that priority will be given to combat supplies and not to spare parts. Also consider that you will most probably have to look to your own local defence. The decision itself could fall into one of 4 categories. Repair at first line, to at least minimum user requirement, to allow completing the ongoing mission and possibly one other. Limited first line repair, to enable an equipment to reach second line support under its own power. The equipment is repairable but at second or third line and will require recovery. When the equipment is not recoverable or repairable, allowing for the time, ground and proximity of the enemy, and having gained, where possible, higher authority, cannibalize and destroy. The third and final stage of the battle damage repair process is repair. Whilst watching assessment and decision, you will have noted some of the damage caused to components of various equipments. It has been found that during live firing trials, that equipment subjected to a variety of types of direct and indirect fire tend to suffer similar component damage. It follows then that the repairs needed to be effected to an armoured personnel carrier or a main battle tank will require the same or similar techniques to those required to repair a B vehicle or an artillery piece. The components and systems that will require repair are radiators, hydraulic and pneumatic pipes and hoses, Component casings electrical cables, electronic components, tyres of wheeled vehicles, and running gear of tracked vehicles. There are techniques, materials and purpose-built kits for effecting repairs to these systems and components. These techniques will be dealt with in a series of programs especially dedicated to each specific repair. Before moving on to these programs, it would be useful to look at a few facts and figures which will help lay out the task that you could be confronted with. The repairs which you may be expected to carry out must be quick and reliable, within the definition of an improvised battle damage repair. This is an unconventional repair carried out in a minimum of time and with a minimum of means, to give a limited serviceability to permit continuing the present or subsequent mission. There is no need for the repair to pass any quality assessment standard other than to perform as closely as possible to the role the user requires. The expected workload in time of war is estimated to be battle damage 30%, with normal equipment failure 70%. Of the battle damaged equipment, it is forecast that 25% will not be repairable. 25% will need to be backloaded, and 50% will be relatively simple to repair at first line. To show the usefulness and necessity of what you will be able to achieve using BDR techniques, consider this graph of a large-scale battle simulation involving several combat divisions worth of tanks. The blue line shows that almost the entire force is incapacitated through battle damage, normal breakdown and accidents after 2 days. The green line shows the availability of tanks when BDR is implemented. The yellow line indicates BDR plus replacement of irreparable tanks. Note that the additional increment gained by replacement is small, as not many tanks are totally destroyed. There are a number of rules to be observed when dealing with battle damage. These are: BDR techniques are only to be used when the normal repair system cannot meet operational requirements. Equipment should be repaired as close to the point where the damage was sustained as is operationally possible and technically feasible. The choice of repairs should be carried out in the following priority: repair by replacement, repair by repair, repair by improvisation. A battle damage repair can and should make use of whatever personnel, tools, methods, materials, and other resources that are readily available. These include shortcuts, substitutions, interchange, cannibalization, and bypassing of components or subsystems. A battle damage repair is to restore an equipment to an operational capability needed in the ongoing battle. Battle damage repair techniques are not to be used in peacetime. Finally, what you have been watching has been preparing you for what will ultimately be your real role. Remember, people's lives will depend on your technical expertise and ingenuity. Assessment of battlefield damage from enemy fire, accident, or normal breakdown must be accurate. Estimates of time and the durability of the repair must be realistic. Most of Russia suffers from very severe winters, and history shows that in times of war it has worked very much to their advantage. Because of this, it is almost certain that any conflict with Soviet forces will take place in winter conditions. This adds a further dimension to considerations on battle damage repair. The intention of this program is to show the added problems of adverse weather conditions. These scenes are from a winter exercise in Norway. It should be remembered that the Soviet forces would have to secure the Baltic coast at an early stage in order to maintain freedom of movement of shipping. This beached armoured recovery vehicle, although not battle damage, is of prime importance, and its recovery is of top priority despite the dreadful conditions. In any battle group situation, assessment decisions on your course of action and subsequent action must be carried out in the minimum of possible time. A large proportion of battle damage occurs as an indirect result of hostile action. Under extreme stress, people will make mistakes that they would not make under normal conditions. Being nervous, a driver will take any evasive action without thinking of the consequences. Whether or not recovery should be effected at the time will have to be weighed against other priorities. In a battlefield situation, there will not be time or opportunity to find or move to a comfortable or convenient working environment.
Okay, can you turn the wheel now?
Although this is only a hold exhaust, fumes into the cab make this priority vehicle otherwise unusable. The repair is being effected with part of the cook's asbestos blanket. Hopefully you will not be forced to go so far as to rebuild a battery post under battlefield conditions. This sequence does, however, demonstrate a simple and readily available source of heat for soldering. It is using a carbon post from a dry cell battery and the charge within the battery as a source of power. The kit to be carried on every Foden vehicle for puncture repair should consist of nylon reinforced plastic core, bonding compound, dilution fluid, and a needle. All other items are already on the CES of the vehicle. The cause of this puncture was obviously a 4-inch nail, A mental note must be made of the angle of the puncturing object when removing it from the tyre. The needle is threaded with the required amount of loops. It is aligned at the correct angle and dipped into the compound, and then using the correct angle pushed firmly and fully into the hole. It is then slowly withdrawn until the needle eye is visible with approximately 12 to 17 millimeters of cord protruding. The cord is then cut to release the needle, and the ends are then trimmed to approximately the same length. This shot shows the repair from inside the tyre. The bond is completed after inflating. Heat generated by the vehicle being driven will also help this process. The wheel must be horizontal so that the tyre will seal correctly. It is then inflated to approximately 10 pounds per square inch. The stabilising leg and gum plank shown here are used to prevent accidents. Leak detector dilution liquid is sprayed on the repair. The detector will turn white should the repair still leak.
REME harness systems are designed from the initial concept stage to provide the user with a fully repairable and maintainable system to meet all the quality requirements of the modern military environment. REME has developed a range of products and repair technologies to form the basis of a repair and maintainability philosophy. This repair philosophy has been incorporated into the harness systems designed and manufactured by REME in their role as a member of the Challenger 2 team. REME's range of heat-shrinkable splices enables simple and effective repair of primary wire. Where a number of splices need to be carried out, there is no significant increase in cable bundle size. Where no heat is available, REME's range of sealed insulated crimps provide an effective method of repair. Where screened components are damaged, repairs can be effected using heat-shrinkable solder shields to reinstate the screen integrity and seal the joint. An alternative method would be to use REME's range of flexible screen splices. These techniques allow repair of even the most severely damaged cables. Where the cable's overall outer screen is damaged and no end access is available, screen integrity can be reinstated using a braid bandage. To ensure an environmental seal on the completed repair, adhesive tape is positioned on the cable jacket. Using REME's range of high shrink ratio tubings or self-amalgamating tapes, the cable jacket can be repaired, giving a true environmental seal. Where the cable is totally severed and components may be positioned onto the cable, repairs are quick and simple. Screen integrity is restored using slide-fit braid and solder sleeves. Environmental sealing is restored using high shrink ratio adhesive lined tubing. REME's termination systems, using spin coupling adapters and heat shrinkable molded parts, allow easy access to the rear of connectors for repair purposes. Wire loops are included during the initial design phase to provide up to 3 reterminations of each contact. The adhesive bond between the molded part, adapter and cable is unaffected. The primary wire identification system is explicit in referring each conductor to its connector location. REME's heat-shrinkable convoluted molded parts allow access to the rear of the connector without the need for any specialized tooling. In some instances, access to the rear of the connector may be gained by releasing the spin coupling adapter and pulling the connector forward. Where REME's high-performance screened terminations are used, a cold repair can be effected by removing part of the cable jacket, loosening the spin coupling adapter, and pulling back the termination assembly. Environmental sealing may be reinstated using the range of heat-shrinkable tubings and tapes. Using simple techniques and minimal tooling, REME's repair and maintainability philosophy provides the designer and user with a cost-effective solution to meet the maintenance requirements of today's modern equipment. Better Ways of Doing Things by REME.